Okay.
Okay, cool. Because I hope that you can.
Okay. So today we'll talk about the advanced power side channel attack and the cache side channel attack, also DMA attack. 3 attacks. So this is the outline for today's lecture, and especially for power side channel attack, you will learn high order attack and high order countermeasures. So what this high order means, I will explain soon. Okay, so this is what we had last time. That's the end of story for last Monday. Last lecture. So we talk about threshold implementation. Right? Threshold implementation can offer provable security for one level of nonlinear function, even with glitches. Right? So this is just an example for when you share 1 bit information into 3 shares, then each nonlinear operation will take at most 2 shares. Right? This is what we learned last time about non-completeness. Right? This is called first order threshold implementation, which is provably secure against the first order attack.
What x1, y1, and z1?
So here x, y, z just is the input of this function, and each value is shared into 3 shares: x1, x2, and x3, and the y shared into y1, y2, and y3. So this share here means that you XOR x1, x2, and x3 together, you will get x. Yeah, but if you only take 2 of them, you cannot get any information about x. So the intuition about this first order security is that no single wire carries any non-masked or non-randomized information. And the order of attack is defined to be the number of intermediate values that attacker needs to predict in the attacks. So for example, here, if the attacker only predicts 1 value here, then because no single wire carries unrandomized information, so essentially the attacker cannot predict and then cannot predict the power consumption and compute the correlation. Okay, what's the question?
Why, if I took 2 wires, then I can recover the security?
Yes.
My
Yeah.
question is, if the adversary focuses on 2 wires,
Yeah.
then he can recover the security. Why?
Yeah, because if you focus on 2 wires, then the 2 wire will carry information, the complete 3 shares of 1 bit information. And that bit information is what you want to protect. Right?
Correct.
You are testing me? Okay, so do you still have a question?
No.
Okay. So what means high order attack? So if several intermediate values can be used to formulate the hypothesis, then the corresponding DPA attack are called high order DPA. So for example, if we can combine the leakage of function S1 and S2, then it is called second order attack because we are focused on 2 functions. So right now we only talk about the second order attack. So a second order attack just simply applies a first order attack to the pre-processed traces. So suppose that you are attacking a masking scheme, which means all the information is shared into 2 shares, and U is the information, the 1 bit information, and it shared into 2 shares, UM and M. Okay? So attacker just choose 2 intermediate value UM and M as attack target. Since mask M is a random number, we do not know either UM or M, but we can predict the value of U, because after we guess 1 key, we can predict the value of U. which is equal to UM XOR M. But U doesn't appear in the implementation at all. Okay? So we record the power traces and do the pre-processing to the trace, and we map U to the hypothetical power consumption value H. For example, we can use the power model we talked about on Monday, right? The Hamming weight and the Hamming distance model to get a predicted or hypothetical power consumption value. And note that here, we can calculate the value of U without knowing the mask M, right? Because mask M is the random number which is generated in runtime. And in the end, we just need to compare the hypothetical power consumption with the pre-processed traces by correlation coefficient. This is similar to what we did for first order attack. So essentially here is, because we cannot predict either UM and M, but we can predict the combination, some sort of combination of these two as U. So we also need to combine the information leakage from the traces. That's why we need to do this pre-processing. So how to do this pre-processing? So use the example on previous slide. If the computation of UM and M are in different clock cycles, then we need to combine the sample points in different cycles. This usually happens in software implementation. And if UM and M are computed in the same clock cycle, then we need to combine the sample points in the same clock cycle. Right, so there are several different ways to combine or do this pre-processing. For example, we can get the product of these two sample points, or take the absolute value of the difference, right? And also maybe take the squaring and take the sum. So there are usually these the four very common pre-processing technique for us to use. So the methodology of second order attack can be even extended to higher order. So how can we get the protection against this kind of high order attack, right? Because right now this first order structural implementation doesn't work anymore, right? It can be attacked. So how to do that? We have high order countermeasures. So for example, disorder TI, which is disorder structural implementation, right? So the only difference between low order TI and the high order TI is that for disorder TI, you need to satisfy the disorder non-completeness, which means any combination of up to D component functions, yi of y, must be independent of at least one input shares. Like when we talk about the first order TI, then so you just need to replace that D by 1. Then you can get this definition. So there is also one theorem about there always exists a disorder TI of a function of degree T that requires T times D plus 1 input shares, and the input share select the T output shares. So here is just one example of second order TI of function. 1 XOR A XOR B and C. And here we need 5 input shares and 10 output shares. So if you compare with the theorem we have, right, the T here, because here we have B and C, so the degree of the function is 2. And D here is 2 because we want second order protection, right? So T times D plus 1, which is 5. So you can get it with 5 input shares. And by the theorem, the output share can be even more, right? So it's a 5 select 2, which is 20. But here we are lucky. We can satisfy this second order non-completeness by these 10 output shares. But sometimes you need to go higher. So it completely depends on the function. So the problem is, can we do better here? Because in order to protect the second order attack, we need so many shares. That's not very efficient, right? So can we do better? So for this, domain-oriented masking, this is another technique which is published last month. So this is state of the art. So it requires D+1 input-output shares for disorder protection for functions with any degree. So the degree doesn't matter anymore. So the key idea of that is it divides the computation in different domains. So for disorder protection, we need D+1 domains. So that's enough for the protection, because if you only have access to D domains, then you always miss one domain information. Right? So the idea is share every bit information into different domains. And here, this is one example of AND gate, which is first order secure. This is just still first order secure. Right? So if we write out here, we have this domain A on the left and this domain B on the right. And this Z0 is a random number. Okay? So if we write out the function for this AND, it will be these 4 terms. This one, this one, this one, and this one. Notice that these two are inner domain terms because they all belong to either domain A or domain B. But these two are cross-domain terms. That's why if you have cross-domain terms, then you need to always XOR with a random number to kind of add the randomness into it again. So this is how it works for the first order secure AND gate. Then how about the second order protection? If you write out the formula, it will give you these 9 terms, and the 3 of them is inner domain terms, and the 6 of them is cross-domain terms. So notice that for each cross-domain term, you need to add 1 random bit. Right. So in the end, this AND gate will look like this. Notice that here we have flip-flop. Do you know why? Ha!
We want to prevent the glitches.
Correct. So in the last slide, we had in last lecture, we talked about we need to insert one level of register between any nonlinear functions to stop the glitch. This is the same thing. So we need to insert the flip-flop, which is also registered, to stop the glitches. So this methodology can be generalized to any disorder protection with D+1 shares.
Can you little bit explain what is domain here?
What domain means?
Yes.
We just manually partition it into different domains. So here, see?
So the calculation, how you...
Calculation?
Yeah.
So for this one, means this term. Right? This is the inner domain term, because the import belongs to domain A. Right? Huh?
So if I had, so this would be like if I had a 6-bit number, and I assigned 2 bits AX, AY, 2 bits BX, BY, 2 bits.
No. Here, this AND gate only perform the operation of 2 input AND, which means 2-bit input, 1-bit output, which is the AND of these two.
Okay.
So every bit needs to be shared into 3 shares and separated into 3 different domains.
why I do not have the flip-flop for the inner domain?
No, because for inner domain operation, everything is in the domain itself. So you don't have cross-domain or information. So no matter how you do computation in the domain itself, there is no information leakage. There still have a dotted registers over there, but that's just for the timing, because you want to get the output at the same clock cycle. But that's not for security reasons.
So it means that if I sum up on the AQ, EQ, and CQ, then
Yeah.
I will have like a and B one.
Not A and B. So here we have one bit X, one bit Y. Bit X is shared into AX, BX, CX into ABC3 domains. Y is,
You split the secret S into 3 shells,
yeah,
and you also borrow some random numbers like Z0, Z1.
Yeah. Z0, Z1, and Z2. You need 3 random number.
Then how I can reconstruct the X and Y value?
Reconstruct the X.
EQ,
No, you don't reconstruct the X and Y. You reconstruct X and Y.
Yeah,
Yeah.
and Y.
X are AQ, BQ, CQ together.
Just saw them together.
Yeah.
Okay.
This is still the same. Right. Same color. So if you can look from the formula, right? If you XOR these 3 together, essentially, yeah, XOR all these 9 terms together, right? And then,
Get it all.
yeah, this random number will be cancelled out, right? So it is
Okay.
this and operation. Correct? Good? Okay, so we finished our topic about the power side channel attack. Right now we are going to talk about cache side channel attack, which is a pretty different one. So cache side channel attack, why we will have this problem? Because in the modern computers, we have cache in the processor. And the data presented in the cache can be accessed faster than from memory. So we have cache initially for performance purpose. And for multi-level cache, data accessed from L1 cache has lower latency than from an L2 cache. But the cache interference and the time difference for the access patterns leaks information. It will leak the information about certain memory content exists in the cache or not. And it will also leak, for example, say it shows that the data has been accessed recently because the data is in the cache. It means that the data has been accessed recently. So this attack is useful to find keys for encryption process. So let's start with one example. It's called the evict and time attack.
So how do you do cache side channel attack? You just you send challenge and get response and calculate the different time step between two.
Yeah, kind of, but you will learn it right now. Right? There are many different ways to do cache side channel attack, but the key idea is that you want to use some way to use this cache interference to figure out whether that data is in the cache or not.
How? Can you give an example?
Yeah.
I'm going to give you an example for this whole lecture.
For what?
I will give you many examples in this lecture. Okay. So evict and time. So suppose we have one cache and one main memory, and the cache have 4 sets. And this is the mapping from the main memory to cache. And we have victim data and attacker's data. Suppose the attacker wants to know if this address 1000, which maps to set 1, was accessed. So he first triggers encryption and times it. So it means that he first triggers the victim process and times the execution of that program. And then attacker evicts everything from set 1. He runs the encryption again.
But how can an attacker can control the cache mechanism?
No, attacker doesn't control the cache mechanism. What do you mean by control the cache mechanism?
You said attacker evict set 1.
By sending their
Yeah, but
all data to the cache.
yeah, the attacker reads lots of data that will fill this cache.
The attacker needs
Needs to know which data maps to which cache line, right?
yes.
Yes, they need to know. They have some way to know. Yeah, because this cache set number is in the virtual address, and especially it's in the offset of the virtual address. So if the attacker can control the address that it is accessing,
That's the problem. How can an attacker can control the virtual address? He must have a administrator privilege. So if an attacker is has administrator privilege, so he can get access directly to the victim data without
Maybe
yeah, that's a good question. So in the case that these two processes are in the same operating system, I don't have a good answer to it, but later on we will talk about the process are in different operating system, in different virtual machine.
maybe the adversary has to characterize the software of the victim. The only thing I don't know is I don't know your secret key. So like if I characterize the software of the victim,
But
I can know what is the virtual address.
the question is, if you know, if you can control the virtual address, it means that you have access to the memory, and you can directly read the memory with the victim's data in the memory, and you don't need to go through.
What's the people who are not allowed to access that memory, and you cannot read the information from the memory?
But then you have access to the virtual address, and then you know
No, I don't know.
which virtual address mapped to which physical address. It means that you have administrator privilege.
So
In the operating system,
so
there-
somehow like the buffer overflow.
Yes. Maybe we can discuss after Shenglu finishes some more slides.
Yeah.
because this is a class, we want to know stuff, we don't want to just present.
Okay.
Yeah, but the thing is, so the core of your question is that how do we know the physical address from virtual address?
Yes.
Oh,
How do you know that which data maps to
right now I don't have a good answer to it, but right now just assume we know, okay? Yeah, but later on I will talk about another example which tells you how to figure out this address translation by cache attack. Okay, so here he runs the encryption again and times it. And then it takes longer than step 1 because one of the cache line is evicted by the attacker's data. So that's why. So by observing that, the attacker can conclude that the victim has access to this particular cache set. And another example is that the attacker wants to know if that 4000, which maps to cache set 4, was accessed or not. He triggers encryption and this time limit. He evicts everything from that set. He runs encryption again, but he finds that the time is roughly equal.
So actually, by this strategy, I can know what is the virtual address of the victim data. So I just simply go through on the cache line.
Virtual address of victim data.
So I try step by step, and until I got this one, then I know that the address of the victim data.
No idea. Not clearly understand. Yeah.
You get what I want?
Yeah, I think correct. Yeah, that's what we have right now. This one. ANC attack. So this is a paper published last week. So in DSS, state of the art. So in this paper, they use the victim and time attack, which we talked about in previous slide, to attack a memory management unit to break this address space layout randomization completely. So do you still remember this address space layout randomization? Vaguely. It just means that it randomized the address translation from virtual address to physical address. So by this attack, they can figure out how this virtual address is translated to physical address. So the memory management unit of modern processor also has this cache hierarchy in order to improve the performance of page table works. So an evict and time cache attack can detect which location in the page table page are accessed during a page table work performed by this MMU. So for example, on the this x86 64 architecture, this attack can find offsets that are accessed by the MMU for each of the 4 page table pages. Remember? So when Martin talked about this, when he talked about the SGX, right? In this architecture, you need 4 page memory access to figure out the address translation. Right? So this attack is called ANC for short. So first, the flash is part of last level cache, and then times the MMU's page table work performed due to a memory access. So this already finds cache lines of interest in the page table page. Yeah, so I think this also answers the question that you have, how to figure out the mapping from virtual address to physical address. But before this, I don't know how they figure out this, because this is a new paper. Okay. So this is another attack technique called the primary probe. So primary probe consists of 3 stages. First stage primary, which means that the attacker needs to fill the cache set with his own cache lines, and then victim accessing that cache lines or not, right? This is what the attacker wants to figure out. And then attacker access the priming data again. If the victim process evicts any of the cache line that he primed, then the reloading time will be slightly longer because it will incur a cache miss. This is another animation for this. So how it goes. So attacker wants to find if a particular address in cache set 1 was accessed. So he fills set 1 with his data, and he runs the victim process. So here, victim process access cache set 1, right, and evict one of the cache line of attacker's data. And he reloads his data in set 1, and he will have, for example, 3 cache hits and 1 cache miss. So it takes longer than he knows.